Curiosity and observation lead to scientific investigation. When we study nature, we often need to measure size, the periodicity, and the composition of things. The units we use in scientific research often have some sort of meaning. The unit of length, the meter, for example, was originally defined as the distance between the equator and the North Pole, divided by 10 million. The system for quantifying temperature is another good example that makes sense. When ice melts, it becomes a liquid we refer to as water. As we heat water, it ultimately boils to become a gas called steam. These phase transitions occur at specific temperatures. When we divide the temperature difference between freezing and boiling of water into 100 equal units, we get the centigrade scale, centa meaning 100. 0 degrees centigrade is the temperature where liquid water freezes, and 100 degrees centigrade is when water boils. In order for us to really understand viruses, we will need to describe reactions and mechanisms in chemical terms, how a virus is put together, and what enables or prevents it from infecting us. Hence, we must understand the units of chemistry. The basic chemical unit is the atom. All matter is made of atoms. Atoms are made of 3 fundamental particles: the positively charged proton, the negatively charged electron, and a neutral particle called the neutron. Protons and neutrons are of similar mass, while the electrons are about 2,000 times smaller in mass than the proton, yet of equal but opposite electrostatic charge. Protons and neutrons are packed together to form the nucleus of the atom. The electrons form a cloud of negative charges that circle the nucleus. This is the general scheme for all matter, but the world around us is made of different chemical elements that can combine and form molecules. Chemical elements like oxygen, carbon, gold, and lead are made of atoms, of course, but differ in the number of protons they contain. Thus, for example, carbon contains 6 protons, oxygen has 8, gold 79, and lead 82. We define a chemical unit, the element, based on the number of protons it contains, which defines the atomic number for that element. Here is a table called the periodic table, which lists the chemical elements. Each element is given a 1 or 2 letter symbol. Some of the symbols make sense, as the English name of the element corresponds to its symbol. Like carbon is C, oxygen is O, and H is for hydrogen. Although some of the symbols are derived from the Latin, as in Ag, argentum for silver, Fe for ferrum, meaning iron. All the elements are arranged in the table by ever-increasing atomic number. Thus, for example, carbon, nitrogen, and oxygen are elements with 6, 7, and 8 protons, and thus follow consecutively here in the same row. For each element, in addition to its atomic number, the atomic weight is given as well. At first, the weight is close to twice the atomic number, the number of neutrons being equal to the number of protons. However, as atoms become heavier, more neutrons are needed to pack with the protons in the nucleus. Thus, lead, for example, with its 82 protons, needs over 40 extra neutrons to keep its nucleus stable. When atoms mix and bind to one another, chemical compounds, molecules are created. Water is such a molecule in which 2 atoms of hydrogen combine through chemical bonds with 1 atom of oxygen to give H2O, water. As we continue throughout this course, we will encounter various chemical compounds like sugars, proteins, and DNA. However, don't fret. You've just completed a crash course in chemistry. Congratulations! This is just about as much chemistry as you will need for this course. Believe me, If you understand chemical elements, you will certainly be able to follow cell biology. In the next unit, we will begin to explore the world of cells and discover who was first to describe cells and who understood that cells are the units of life.